This is section 6.1, part 3, and we're now going to generalize everything that we've been talking about regarding velocity, position, and displacement into more general rate of change types of situations. So we're going to start here by imagining that we're interested in some general quantity Q that changes over time. Maybe it's the volume of water in a sink that's being filled or something like that, but something that changes over time. All right, in fact, here's a few examples right here, I guess. Population of a cell culture that's growing over time, the amount of a resource that's being produced or consumed, all the kinds of things that might change with time. If we're given the rate of change is always our derivative, so that would be the derivative of Q, or Q prime. Then, if we integrate that derivative, we can do two different things. We can calculate the net change in the quantity of Q, or we can also, this would be a definite integral, or we can also find what's called a future value function. This is the one where we do the indefinite integral, or just the antiderivative, and if we've got some initial conditions, we can solve for that constant of integration. So this is the indefinite integral where we have to solve for C. Just to look at the comparison between what we've been doing and this generalization, take a look at this little table. Our straight line motion problems, the quantity that we were basically working with was a position function, S of t, as opposed to the general problem where we're just saying Q just represents some quantity. The derivative S prime represented the velocity, which is also known as the rate of change of S. How fast position changes is how fast you're going. It's your velocity. If our general quantity is Q, the rate of change of Q would just be its derivative, Q prime of t. All right, let's think back to what we were just doing with displacement. With displacement, we allowed the signs, right, the positives and the negatives, to be whatever they were, and we just went ahead and integrated from start time to end time. And we integrated our velocity function, or our derivative, S prime of t, dt. Using that same thought process, just like this would tell the displacement or the change in position, we could get the net change in quantity by integrating that derivative from a to b, the integral of Q prime of t, dt. So this is the net change in position, which is displacement. This is the net change in whatever the quantity we're working with is. All right, finally we have our future value equations. We know that if we knew velocity, we could get the future value, or the value of the position, simply by doing the integral of the velocity function. Or we could have written that as the integral of S prime of t, dt. And in the same way, the future value of Q of t, would simply be the integral of the derivative Q prime. So the same thing is happening on this side as is happening on this side. This is just the more general way to look at it. Just a little bit of behind-the-scenes geometry here before we try a few examples. Geometrically, the net change in Q over the time interval from A to B would be the net area under the graph of Q prime between A and B. So if we imagine a graph that actually represents not Q, but Q prime. So here's Q prime of t, some function. Then from a starting time A to an ending time B, we know that the integral from A to B of Q prime of t dt just represents the area under the curve. Right? That's geometrically what an integral does. Finds the area under the curve. Think for a moment about what's happening here. It essentially adds up all of the small little changes, all of the little values of q prime over tiny little intervals, right? You could imagine breaking up this interval from A to B into little tiny pieces. And over each time interval, it takes into account how much q is changed in that time interval. And then the integral essentially adds up all of those changes, giving us the net change in the quantity. One quick note about the integrals. Can you see that the units here are consistent with the idea of the net change in q? The derivative would have units of whatever the units are per unit time, so the units of q, like volume units or population units or whatever, but units per time. And then the t itself would have time units. And so we end up with whatever the units of q are when we do this derivative. So that's how much q is changed over that full time interval, and that's going to give us the same units as whatever q was to begin with. All right, let's try a few examples. This first one is starting to get a little old. I guess it's about 10 years ago, but perhaps many of you remember a major oil spill. I think it's the largest one in history. The Deepwater Horizon oil spill occurred in the Gulf of Mexico over a period of 87 days back in 2010, before the wellhead was finally capped on July 15th. During this time period, the rate at which oil was leaking from the uncapped well, in units thousands of barrels per day, can be modeled by the function b prime of t is equal to negative 0.105 t plus 62. Notice, this is the rate at which the oil was leaking, and so it's the derivative. It's a rate of change, b prime, not b itself. Here t represents the number of days since the spill began on April 20th. So in other words, April 20th is being treated as t equals 0. Let's think, before we just jump right into this, let's think for a minute about this b prime. Notice that b prime is a linear function with a negative slope. So the rate at which oil is leaking is actually getting smaller and smaller as time goes on. We're going to see that illustrated in part A here with some specific values. I want to know how fast was the oil leaking one day in, on April 30th, and then just before the wellhead was capped. So we want to know how fast it was leaking, meaning we want the value of b prime. We want the rate that the number of barrels is changing. So one day in, we just want b prime of 1. Plugging in 1 to our b prime equation, of course, is just going to give us, what is that, 61.895? And again, this is the rate of change, so that would be thousands of barrels per day. So on that first day, roughly 62,000 barrels would have escaped. We can keep doing this. April 30th, since we started on April 20th, that would be 10 days in, so b prime of 10. And if you just plug 10 in here, I just did the arithmetic on the calculator, got 60.95. Again, 1,000 barrels per day. And then just before the wellhead was capped, it told us that it took 87 days, so that would be the rate of change b prime on the 87th day. And again, just plugging the 87 in for t, that one gave me 52.865. Thousands of barrels per day. So as we noticed with a negative slope here, we are getting slightly slower in terms of the oil leak rate as time goes on. If you think about it, it kind of makes sense. As the oil is released from underground, the pressure underground would actually get less, and so that would mean that it would push the oil out at a slower rate. And so that would be a reasonable natural phenomenon, meaning that our model is probably not too bad. All right, part B. How much oil was released during the first week of the spill, and then throughout the entire spill? Now, of course, we could say, okay, day 1 it was coming out at about 61.895 thousand barrels, and then we could do day 2 and 3 and 4 and 5 and 6 and 7 and add them all up to get our estimate. But that's pretty time consuming, even for a week, much less having to do that for 87 days. Much more efficient would be to use our net rate of change formula, or net change rather, not rate. So our net change, the amount of oil released for the first week, would be the integral over the first 7 days, from 0 to 7. So this is for 1 week. And we're integrating our B prime. Like so. On these, by the way, these are pretty simple integrals. I'm going to encourage you to, play around with those if you'd like to do them by hand. I did punch these in the calculator just to save us some time. As we go a little bit further, if we get some more challenging integrals, we'll do them by hand. But I'm going to assume at this point that these integrals are pretty much old hat to you. All right, so this one gave me 431.4, and that would be thousands of barrels. Right? This is now how much oil has leaked out, the net rate of change in the amount of oil in that first week. Second part of this problem was how much oil leaks throughout the entire 87-day spill. So all the oil that was leaked from day 0 at the start to day 87 at the end. Once again, we integrate B prime. And this time I got 4,996.6, actually 0.6275 if I keep a few more decimal places. That would be in thousands of barrels. Or if you want, we could actually multiply by 1,000. Moving our decimal plate over 3 places. 4,996, 627.5. It would be just under 5 million barrels that were leaked during that whole overall spill. And actually, if you look up the data on the Deepwater Horizon oil spill, that actually is the estimate that scientists gave for the total amount of oil spill was somewhere in the neighborhood of 5 million barrels. All right, part C. Numerous failed attempts were made to stop the leak. On May 7th, they tried a containment dome. It failed. On May 26th, they tried what's called a top kill maneuver. It also failed. How much oil was released between these 2 attempts? And we can go ahead and include the dates of each attempt in our answer. So once again, we want the net rate of change. We don't want the rate of change. We want how much oil. That's the net change in oil from May 7th to May 26th. So May 7th, let's see, April 20th was our start date. So that would give us, 10 more days of April plus 7 days of May would be T equals 17. And May 26th, again, there were 10 more days of April, starting on April 20th to April 30th, 10 days of April, plus those 26 days of May would be a T of 36. So we'd want to integrate from 17 to 36. We integrate our rate of change function to get the net change in the amount of oil. Once again, not a difficult integral. You could punch it in your calculator or do it by hand. I got 1125.1. And that would be in thousands of barrels. So a bit over 1 million barrels, really, between the two attempts they made to cap off the oil spill. All right, lastly, we want to find the future value equation, B of t itself, and then just talk about the domain of that equation. So our future value is always the indefinite integral. We're just going to integrate our b prime function. Which is going to give us negative 0.105 t squared over 2 plus 62t plus a constant. Or in other words, negative 0.0525 t squared plus 62t plus c. And in this case, we need our initial condition to solve for c. They don't flat out give it to us, but we should be able to kind of figure it out from the context of the problem. At time 0, how many barrels of oil have spilled? Well, at the very instant that the oil spill starts, nothing has escaped yet. So the total amount spilled at time 0 would be 0. And if we plug that in, b is 0, t is 0, we see that in this case, the constant does just turn out to be 0. So our future value equation, b of t, is negative 0.0525 t squared plus 62t, just plus 0, which I won't bother writing. Notice, by the way, that using this equation, we could have, in a very straightforward way, answered both of these questions, right? The amount of oil spilled from the beginning until day 7, and the amount of oil spilled in the beginning until day 87, simply by plugging the t values into our function. So just to verify, let's do the second one. If I did b of 87, okay, there's that 4996.6275, just like we got here. What I couldn't have done in such a straightforward way is to answer this question. This future value equation is always going to measure the amount from the beginning. If I want the amount between two times, the most straightforward way to do it really is with the integral. Now, grant you, I could plug in the 36, plug in the 17, and subtract if I wanted to, but it's probably more efficient to simply do the integral. Okay? So I'm just trying to help you see how all these pieces fit together. All right, let's try another example. So in that example, it was the amount of oil that was changing, the amount of oil that had escaped from our well. In this next example, it's going to be the number of cells that are going to change in a cell culture in a biolab. We start out with a population of 1,000 cells at time t equals 0. Nutrients are added to speed the growth of the culture, resulting in a population growth rate. Notice growth rate, so no wonder it's a derivative. N prime of t is 90 e to the negative 0.1 t, and that's how many cells per hour that this culture is growing by. First thing we want is the change in the number of cells during the first 5 hours. Notice it's the change, not the rate of change. If I want rate of change, I would have used n prime. Because I want change itself, I need the integral n to get n. So first 5 hours would be from 0 to 5. And we'd have 90 e to the negative 0.1 t dt. And again, just to speed things along a little bit, I went ahead and just did the integral on the calculator. You could certainly practice it by hand if you like, but I got 354. And the units here would just be cells. So this culture grew by 354 cells during those 5 hours. In actual fact, of course, since we started to 100, that means there would be 454 at the 5-hour mark. All right, part B. We want the future value equation, n of t. The future value equation is always the indefinite integral. And let's see, we haven't done a u substitution for a little while. Let's just write that up real quick. If I let u be the negative 0.1t, then du would be negative 0.1 dt. And if I divide by negative 0.1, dividing by negative a tenth would be like multiplying by negative 10. So I'd have negative 10 du is equal to dt. And therefore my integral would become, well, let's see here, I'd have 90 e to the u, and then I would replace my dt with a negative 10 du. I'm going to put the negative 10 out here. So I'd actually end up with negative 900. The integral of e to the u is still e to the u, or e to the negative 0.1t, plus c. We'd like to figure out what our c value is, and in order to do that, I'm going to use the initial condition. Our n, our number of cells, is 100 when t equals 0. So, putting in n as 100, t is 0. E to the 0 is 1, so that's just negative 900. Bring that over, add 100, and I'm going to end up with a c value of 1,000. So my future value equation, n of t, is actually going to look like, let's see, here we go, negative 900 e to the negative 0.1t plus 1,000. All right, in part C, we're going to reconcile what we did in part A with part B. Part C says find the number of cells after 5 hours. Well, this is now my equation for the number of cells, so I should just be able to do n of 5. So if I plug 5 in for the n here, let's just see what we get. We get about 454. I'm rounding to the nearest whole number since these are cells, or whole individual cells, so about 454. And as we pointed out before, notice in part A, we said that the culture grew by 354. When we take that 354 and we add the 100 that we started with, we get that 454. And so all these little pieces of our puzzle are making sense. They work well together. All right, using our future value equation, we can now easily answer questions like part D. How many cells will there be after 15 hours and after 25 hours? Notice I don't want the change in the number of cells. I want the actual number of cells. So when I wanted the change in the number of cells, I used the integral. When I want the actual number of cells, I'm going to use n. So in part D, we just want n of 15 and n of 25. And of course, that's pretty straightforward now. We're just going to plug the 15 in, plug the 25 in. I just did that behind the scenes so you wouldn't have to watch me punch buttons. When I plugged in 15, I got 799. And when I plugged in 25, I got 926 cells. All right, last part of this one, E, says to discuss the findings in part C and actually part D as well, with reference to the graphs of n prime and n. Let's talk about these just a little bit. We have our n right here, and I'll just remind us here that n prime is off the page, off the screen for you right now. It was 90 e to the negative 0.1 t. N itself was this. Let's kind of look both mathematically as well as looking at some of our numerical examples to think about what's happening here. Right? Let's think for a moment about what would happen or what's going on as time moves along. Certainly the number of cells is growing the further along we get. This population of cells is certainly increasing in size. But how is it increasing? Notice here, in this 10-hour period, we went up roughly 250 or so. But in this 10-hour period, we only went up about 125 or so. So while the cell culture is growing, the rate of growth is slowing. So the first thing I'm going to say, my first observation is, n prime is going to be positive because we are growing in population all the time. But n prime gets smaller over time. Right, the growth rate is decreasing. It was going up faster here than it was later on. So the growth rate decreases. Logically, again, if you think about the situation, this should make sense, right? They added some nutrients to speed the growth of this culture. So right away, that's going to increase the growth rate quite a bit. But over time, as the nutrients get used, the growth rate's going to decline. All right, what about n? Well, let's see. N itself starts out at 100, and then it gets bigger. First, it gets bigger quite quickly. It continues to get bigger, but the rate at which it gets bigger slows. So n increases at all times, but the rate of increase slows. All right, let's get a little bit mathier with that. Let's think long term. What's going to happen to both the n prime and the n equation as t goes to infinity? If t goes to infinity, well, let's see, that would become e to the negative infinity, and that limit is 0. So not only is our n prime getting smaller over time, but we now know its limit is 0. Essentially, it's going to stop changing, stop growing. What about the limit as t goes to 0 of n itself? Well, by the same logic, here's that e to the negative infinity. I'm sorry, I keep writing t goes to 0, but I really mean t goes to infinity. My fault. E to the negative infinity, again, goes to 0. So all you're going to have left is the 1,000. This population is going to stop growing. The rate of change becomes 0, and it levels off at 1,000. So if I were to draw myself a couple of graphs, here's one for n prime, and there's one for n. Even without graphing on the calculator, n prime is positive and gets smaller over time, going towards 0 as t goes to infinity. My n prime graph should look like this. And notice that's typical exponential decay. The n graph increases at all times, but increases more and more slowly and levels off at 1,000. Starts at 100, right? So n must look something like that. Now you can verify those by plugging these two equations into your calculator if you want to, but just based on our analysis, it really has to happen that way. All right, let's take a look at example 3. We're still in population, but this time we're a population of a community of human beings, I think. Actually, maybe it's not human beings. Sorry, it's foxes, isn't it? Population P of T of a community of foxes fluctuates on a 10-year cycle, sort of a natural variation due to predator and prey relationships. Initially, there were 35 foxes. The growth rate, so notice the growth rate is a derivative, P prime, is 5 plus 10 sine pi t over 5. We would like to go ahead and, first of all, graph the P prime equation itself, and then talk about if the population is growing or shrinking at various times. So I'm going to go ahead and say, this is a little bit more of a pain to draw. Let's graph it on the calculator. By the way, make sure you're in radian mode when you do this. And in my window, I'm going to go, we'll assume time is positive, so I'll go from 0 to, let's see, a 10-year cycle. Let's go at 20 years. Let's look at 2 cycles. Scale of 1 is fine. And P prime is the rate of change in the number of foxes. I'm going to go from negative 10 to 10 and see what happens. Nope, I should have gone a little bit bigger. We'll go negative 10 to 20. There we go. So I will just generally sketch this, but I'll rely on my calculator for a more accurate graph. Why not 20 years? All right. We would like to know, is the population growing or shrinking at the end of 3, 5, and 9 years? And of course, the growth or shrinking is the positive or negative rate of change. Population is growing if P prime is positive, shrinking if P prime is negative. So if I just go ahead and use my calculator, I've got the graph of P prime in here. If I ask for the value, put that over where you can see it, sorry, at x equal 3, which is really t equal 3, it's about 14.5. Now, of course, I could have done that by plugging the t value of 3 in here. This is just a little faster. Could have also used a table. The units here, rate of change, would be in foxes per year. So at the 3-year mark, that population is growing by 14 or 15 foxes each year. What about the 5-year mark? The 5-year mark, we're here. Notice our P prime is still positive. We're still on the top here. In fact, it's exactly 5. So after 5 years, the population is growing by 5 foxes per year. And so in both of these cases, the population is growing. But when I look at P prime of 9, P prime of 9, it's right down here. Notice that we've dipped below the axis, and the value of our P prime is now negative, about negative 0.88. So our population is declining by roughly 1 fox every year. All right, part B. We would like the net change in population. So net change, we can use an integral to do that over 3, 5, and 9 years. So for the first 3 years, I'll just do the integral from 0 to 3 of my p prime equation. And again, I'm just going to use a calculator to speed this along a little bit. I got about 35.8. Over the first 5 years, same idea. We'll integrate from 0 to 5. And I pre-plugged that one in the calculator for us as well. And I got 56.8. And then finally, the first 9 years. Integrating from 0 to 9, I got 48.0. Okay. Now this is the net change in population. So this is an actual number of foxes. Here we're saying that over the first 3 years, the population grew by about 36 foxes. Over the first 5 years, it grew by about 57 foxes. And over the first 9 years, it grew by about 48 foxes. Okay. If you're thinking, wait a minute, how could it have grown more here than here? Remember, the population was growing all the way through the first 5 years, so we kept having greater and greater increases in the number of foxes. But in year 9, it was actually shrinking, so our population has shrunk some from year 5 to year 9. All right, in part C, they're saying, looking at our graph of p prime, right, this is t and p prime, what can you predict about the long-term behavior of the population? Well, if we think about this a little bit, everywhere that there's a positive value of the derivative, p prime is positive, p prime is positive, and it would just start all over again, right? The population would be growing at all of those times. It's only for these short little bits of time that our p prime, our derivative, is negative, and p is shrinking. So in this case, we can safely say the population grows a lot more than it shrinks. Think area under the curve here, right? A lot more area under the growth parts than there are in the shrinking parts. So overall, even though there's going to be some fluctuation, the population is going to go up and down a bit. Overall, long term, this population is going to grow. So I'm going to say the population fluctuates some, but grows overall. Long term. And again, when we say grows overall, that's because p prime is positive a lot more than p prime is negative. All right, in part D, we're asked to find the future value of our population. We want the p equation, so that's the indefinite integral. And then we'll kind of compare our prediction to what we see from that actual equation. So here we go. P would be the indefinite integral of our p prime the integral of 5 is just going to be 5t. And then I'm going to go ahead and I'm going to concentrate on just this part to do a little bit of a u substitution here. We would have u equal to pi t over 5. So du would be pi fifths dt and 5 over pi du. would equal dt. So I'm going to have, I'm going to pull the 10 out here, and then I'll have the integral of sine u, and then the dt becomes 5 over pi du. Let's see, that's going to become 50 over pi, and the integral of sine is actually negative cosine, and it'll be the cosine of u, which is pi t over 5. So there's my population equation, but I still need to solve for the c value. Remember that we already knew that we started with 35 foxes. So I'm just going to go ahead and say I already know that at time 0, my population was supposed to be 35. So t is 0. Cosine of 0 is just 1. So I'd have 35 plus 50 over pi is my c value. You can get a decimal for that if you want, or you can just leave it like that. And that means that p of t is 5t. Oops, here, sorry, 5t minus 50 over pi cosine pi t over 5 plus 35 plus 50 over pi. And that's my future value equation. If I plugged any t values in there, it would give me the prediction for the population at that particular moment of time. All right, just to verify what we said in part C, let's go ahead, and part E just says to compare the prediction with this equation. I don't have a lot of space left to write, but I'm going to graph on the calculator anyway. We're going to go ahead and graph our population equation and just verify that it really does fluctuate, but overall, long term, we should see growth. So I'm going to type that equation into my calculator. All right, so there's my P of t equation. Just plugged into the calculator there. And I'd like to graph this. I'm going to go ahead and start with the 0 to 20 that we had before, but we know we started with 35 foxes, so we definitely need more than 20 here. Let's try 200. Okay, there's that fluctuation, right? Went up, came back down a little bit. Up, comes back down a little bit. So the fluctuation that we predicted is definitely there. But notice that the overall trend is long-term. This thing is going to grow. And in fact, if I were to change this to maybe 200 years, so letting my t-values get much bigger, let's see, I'm going to change that to 500. Notice now we see all those little fluctuations. They appear much smaller, and it's very clear that the trend is overall growth. All right, we have one last example to look at in this section. This is more of an economics type of example. If the cost of manufacturing X items is given by a cost function C of X, then what's called the marginal cost function, C prime of X, of course represents the rate of change of cost. Marginal cost is just a vocabulary term from econ. As such, C prime of a particular value A actually provides us with an estimate of how much it's going to cost to manufacture the next item, the A plus first item. So we know the cost of manufacturing A items. The rate of change says, hey, this is how much that cost is changing per item. Therefore, it gives us the cost of the next one. Suppose, for a problem that we're doing, The marginal cost for the production of a particular calculator is given by this C prime is 200 minus 0.05x. Part A, we want to estimate the cost to manufacture the first calculator and the 101st and the 1001st. Okay? And in order to do part A, I'm actually going to use this idea. So we're going to do it that way. So if I want to estimate the cost to manufacture the first calculator, my A would actually have to be 0. And if I were to take C prime of 0, just plugging 0 in here, then of course I'm going to get 200. Our estimate is it costs $200 to make that first calculator. To make the 101st, so 101st, A would be 100. If I just do C prime of 100, plugging 100 in here, I get 195. Okay. Typical, right, in manufacturing, often the cost per item gets lower when you make more items. You can buy things in bulk, processes are more efficient, etc. And then that 1001st, now our A value would just be 1,000. And if I plug that in, C prime of 1,000, turns out to be 150. So we're starting to see some clear cost savings. Each calculator is getting cheaper to make as time goes on. All right. Part B. I now want to not talk about the manufacture cost for a single calculator, but the whole group, all of the first 100 calculators. How much is it going to cost? And again, I really don't want to figure out how much for the first, how much for the second, how much for the third, and add them up. Instead, a much more efficient way to go would be to integrate from 0 to 99. Again, 99, right, would be 99 plus 1 would give us that 100th calculator. We'll integrate our C prime. And again, not a difficult integral to do, but just to save us time, I plugged it into my calculator, and I got $19,555. Part C, how much is it going to cost to manufacture calculators number 901 through 1000? Let's see, calculator 901 would be an A value of 900, and calculator 1000 would be an A value of 999. And again, rather than adding them all up individually, much more efficient to simply integrate. And I came up on this one with $15,100. So notice that both of these were manufacturing 100 calculators. This is the first 100, this is the 901st to 1000th, and there's a significant cost difference in our manufacturing as our manufacturing processes have gotten more efficient. All right, the last question, find that future value equation. Again, as soon as you see future value, that's that indefinite integral. So we're going to do the indefinite integral of 200 minus 0.05x dx. That's going to give me 200x minus 0.05x squared over 2 plus c. So c of x is 200x minus 0.025x squared. Now let me call this a plus k. I'm using c two different ways here, right? Call it plus k this time. We are told that the overhead costs for this manufacturing plant are $50,000. So what that's really saying is that even if I don't manufacture a single calculator, if x is 0, my cost is still going to be $50,000 just in overhead to keep the building and keep the lights on and pay my employees, I guess, all that kind of stuff. So I know that 50,000 equals 200 times 0 would be 0, minus that x squared makes that a 0 as well, giving us a k value of 50,000. And so my future value equation is 200x minus 0.025x squared plus 50,000. All right, so rate of change, net change, future value are the concepts in this area, and that brings us to the end of 6.1.